Okay, welcome to GeoTutors. We are continuing the third part of our series on qualitative interpretation of magnetic method. Now, a man known as Lionel Thomas Peter Elphinstone developed a method, an upslope method, that is used to determine the depth of a magnetic source. Okay, and we're going to look at, and that's the name of the method is called Peter's half-slope method. I'm going to look at how to use Peter's half-slope method to find the depth, to estimate the depth. You know, when you're talking about qualitative, we're not getting the exact, we're getting the estimate. We're trying to estimate the depth. So it's not exact, so I just want to have an estimate. So it's like when you're having like a rough check or something. So let's draw our array data. Good. So before I even draw, there are some things I need to explain, just some basic calculus, just basic calculus. Don't be afraid of calculus. So now, if we have something like this, if you draw a graph moving this way, can you see the graph is increasing in this manner. When the graph turns, that point where it turns is known as the point of inflection. What did I say? The point of inflection. The point of inflection. The same way, if this graph continues to decrease, I now choose to take a turn of increment. This piece is also called the what? The point of what? Inflection. So it is this point that we are going to use to determine our half slope method. We're going to use this point of inflection. Okay? So let me come again on it. When you have something like this, your graph is increasing and it chose to what? Take a turn to what? Decrease. What is happen? That point is known as what? The point of what? Inflection. The starting point, the ending point. Good. So let's apply our slope method. So as the head of it is a slope, so which means I'm going to draw a tangent at the point of the inflection. I'm going to draw a tangent line. Two parallel tangent line of two inflections. Let's just imagine you have something like this. Okay. So given that we have something like this, right? It's something like this. Good. And we want to draw let me draw this guy very well. Good. So our point of inflection is where you see that turning point. See, it's increasing here, turning point. It's dropping here, trying to increase the turning point. So you're going to pick the two turning points here and here. I see. Those two what? Turning points. So you're going to pick those two turning points and use your ruler to draw two parallel straight lines. Two parallel what? Straight line. Okay? Okay. It has to be parallel. Can you see it? Both of these lines will never meet. It's how you what? Parallel. So the first step is at the point of inflection, you draw that line. At the point of inflection, you draw the what? The other line. Good. So the next step now is just take a horizontal distance between both lines. Horizontal what? Distance between what? Both lines. And that will give you what? Our x half. This is known as the what? The Peters half slope method. Peters half slope method. So depending on what you have in the subsurface, so let's say when you count this stuff, let's say what you have is x half is equals to uh, let's say 25 meter, for example, and let's say where you are going to calculate is Z. Let's say what we assume here is 2 points. Is a sphere. Let's say we assume that in this place is a sphere, for example. So say Z is equals to 2.5 x half. Z is the depth. We want to estimate the depth. So we always assume the geometry. We are assuming the kind of geometry that we have. So we assume that it's a sphere 2.5 times x half. We assume that it is, oh, sorry. So that's for half width method. Now, for Peter half slope, for Peter half slope, remember that for half width method we said z equals to 0.5, but for Peter half slope is different. What you try to do is to check how thin, thick, or intermediate the anomaly is. But most of the time we use the thin. So we say something like this: x is equals to 1.2 d. X is equals to what? 1.2 d. X is what we have here. This guy here is our what? Our x, our foot. Okay, is our x. Then any answer we get here, we say, let's say like, if x is equals to, if x here is equals to, let's just say 1.2, for example, 1.2, right? Let's say after measuring this, the distance from here to here, you have to, it's up to scale. You have to check your scale. So 1.2 is equals to what? 1.2 d. I put about 1.2, I put about 1.2, then d equals to what? Diameter. So this is the Peter half slope method. Okay, assuming it's for a thin geometry. So for half width, we checked for the geometry of the sphere. For Peter half slope, it's a method that